Right, in this video we will look at determining the hardness in water sample. So a few things you must know there. Hard water is water which is difficult to form a lather with a soap. Now in this video or in this experiment, what we do is we express hardness in terms of parts per million of calcium carbonate, CaCO3. Now technically that is not correct because calcium carbonate is insoluble in water. It doesn't dissolve in water, but it's just by convention. It works out handy as well because the relative molecular mass of calcium carbonate is 100. So the sum, this is an experiment to measure the total hardness of a water sample, and total hardness means the sum of the concentration of calcium and magnesium ions in water. So it doesn't differentiate between a calcium ion or a magnesium ion, between calcium chloride, calcium sulfate, magnesium chloride, magnesium sulfate, or calcium hydrogen carbonate. And calcium hydrogen carbonate is the one that's responsible for temporary hardness. So a few wee things that we might need to know from water previously. How do calcium ions get into water? Now how calcium ions get into water, calcium carbonate, which is my limestone, CaCO3, reacts with water and carbon dioxide. Now them two things form carbonic acid. The carbon dioxide produced, say, from the fossil fuels burning, and the water just up in the atmosphere forms carbonic acid. Now when they react, they produce calcium hydrogen carbonate. Now calcium hydrogen carbonate there is soluble, and since it's soluble, it's going to release these calcium ions into the water. Yeah. What else was I thinking there? Also, that reverse equation's important. So how to remove temporary hardness. Oh yeah, that's what I was thinking. Anything with calcium hydrogen carbonate is temporary hardness. So hardness caused by calcium hydrogen carbonate is temporary hardness. And if we boil that calcium hydrogen carbonate, or water containing calcium hydrogen carbonate, we release CaCO3, water, and carbon dioxide. The reverse equation is that there. So if we add on heat, and what's the CaCO3 appears as is limescale or fur in your kettle, especially in the hard water regions of Ireland here. So in this experiment or titration in question 1, we measure the total hardness. And what we use there is a standard solution, i.e. a solution whose concentration is accurately known, of edta. Now edta, you do need to know what edta stands for. It's ethylene diamine tetraacetic acid. So you've got a standard solution of that, maybe 0.1 molar. And we put it in our burette, and you need to know the standard things. How do you prepare your burette? Rinse it with deionized water. First to remove your impurities, and then rinse it with your edta solution to coat the side, and then fill it above your 0 centimeter cube mark. Ensure it's vertical, run into a beaker to ensure the portion below the tap's filled, rate at eye level until the bottom meniscus rests at the calibration mark or rests at the 0 centimeter cube mark initially, all that sort of jazz. So your edta goes in the top. Now in the conical flask we have our water sample, which presumably will have calcium or magnesium ions. So we're going to test for these calcium or magnesium ions. You have an indicator, and the indicator in this case is either known as aerochrome black tea or solochrome black. And you've got pH 10 buffer. Now when all them things are mixed, initially you get a wine red colour. So if we have an equation, now they'll always give you this. So this H2Y2 minus, that could various versions of representing it. That's my edta. Here's my hard water sample. I'll just represent it with your calcium ions. And what this is known as, it's known as a complexometric titration. Complexometric, it forms a complex. So your edta wraps itself around all these calcium and magnesium ions until they're held together, and then the next drop of edta into this indicator will cause it to go dark blue. So not until all your calcium ions have been wrapped around into this complex does the next drop there form a dark blue colour. And here is going to be my edta complex, my edta complex. And I can see there I've got H plus ions produced, your H plus ions. I'm thinking there of my arrhenius acids there. So I'm producing hydrogen ions, hence why I need my pH 10 buffer. So it allows the indicator to work properly Otherwise I get a poor endpoint because it would complex, your EDTA would complex with other ions, which may be in the water. Now we'll have a wee look at 2022. Starting to get a hang of it, I think, with this Chromebook slightly better. So you can go through the general ones yourself. Oh, look at the feck all room. I'll do the bits at the top. So it's a 1-to-1 ratio if you looked also at that equation on the previous page. So a 1-to-1 ratio makes the calculations easy. So I'll start off, write my TitCon. And I'll write it in above it because God knows I don't want to cut off anymore like you'll see in the equilibrium calculation. So on average, 9.2 centimeters cubed less of the 0.01 molar EDTA solution was required to complete react with 25 centimeters cubed portions that have been passed through the deionizer with 25 centimeters cubed of the original water sample. Calculate the number of moles. I don't know because I've cut off the first bit, what they're on about this less. I'm just going to do these questions and hope that they work. Preparation is poor. So I'll just go into E part 1. Calculate the number of moles of EDTA and 9.2 centimeters cubed of 0.01 molar. Now once I see that big M, what does it mean? It means 0.01 moles in a litre. How do I write that in maths? 0.01 in 1,000. And then multiply it by the volume you have. Multiply it by 9.2. Or some of you might have a formula, volume in centimeters cubed by molarity, divide that by 1,000, it's the same thing. But I work with the big M. Work with the big M, you cannot go wrong. And you get 9.2 by 10 to the minus 5 or 0.000092. 2 moles. Next thing, the number of moles of my hardness causing ions that react with this. And this is where we see them as a 1-to-1 ratio. So we have 0.000092 moles also. It's the equivalent number of moles. And then the crucial bit, in how much? In my 25 centimeters cubed. Part 3. The number of moles of ions removed by the deionizer from a litre. So we want to work out the concentration or the molarity. So we've got 0.000092 in 25 and then times that by 1,000. So you could multiply by 40 if you like. And you get 0.00368 moles per litre of my hardness causing ions, whatever it may be. And then the last one, the total hardness removed by the deionizer expressed in grams per litre of calcium carbonate in parts per million. So we've got moles per litre. The big M means moles in a litre if you like. How to go from moles per litre to grams per litre? I multiply by the relative molecular mass. And the relative molecular mass of CaCO3, work it out there, is 100. So calcium is 40, carbon is 12, it's 52, and 3/16 is 48. Works out to be 100. That works out nice because you just have to move the decimal point. Put it in your calculator if you wish. That much grams per litre of my calcium carbonate, which remember doesn't itself cause hardness, and then multiply that there by 1,000 because when you're in grams per litre, to go to parts per million, that's the same as milligrams per litre. So to change grams to milligrams, you multiply by 1,000 and you get 368 milligrams per litre, which is the exact same as 368 parts per million of my calcium carbonate. Now, they could bring in questions like that. If you boiled your water sample, what might happen to the value if it contained temporary hardness? The value would go down. You could end up with 100 parts per million of calcium carbonate. So to work out the temporary hardness, you'd subtract the two figures. Right, hopefully that helps a wee bit.